Printed circuit board. The motherboard is a stack of copper pathways pressed between layers of fiberglass. Every component on it is just talking to another component through those paths. That green coating on the outside protects those paths from oxidation and short circuits. Scratch through it while installing something and whatever that trace connected to stops working permanently. CPU socket. The CPU socket is the single most important mechanical component on your motherboard because it's the one that connects the processor to everything else. Without it, your CPU would need to be soldered directly onto the board, which is exactly what laptops do, and exactly why upgrading a laptop processor is basically impossible. There are two main designs. LGA, which stands for Land Grid Array, puts the pins on the motherboard and flat contact pads on the CPU. This is what Intel has used for years and what AMD switched to with their AM5 platform. The other design is PGA Pin Grid Array, where the pins are on the CPU itself and the motherboard just has holes. AMD used PGA for its entire AM4 lineup covering Ryzen 1000 through 5000 series. The difference matters more than you'd think. With LGA, if you slip during installation, you bend pins on the motherboard. With PGA, you bend them on the processor. Either way, one bent pin in the wrong spot and the whole thing is dead. Intel's current LGA 1700 socket has 1700 of those pins packed into a space roughly the size of a matchbox. Every single one of them needs to make contact. So instead of just dropping a chip in and hoping for the best, modern sockets use a zero insertion force design. You place the CPU in, lower a metal retention plate, and a lever locks it all into place. No pressure required from your end during the drop, which is good because the margin for error on something with 1700 contact points is basically zero. Chipset. Two motherboards can use the exact same CPU, the exact same RAM, and still behave completely differently. That's the chipset. In the old days, this was literally a set of two chips. The North Bridge sat close to the CPU and handled the fast stuff like memory and graphics. The South Bridge handled everything slower, like USB ports, audio, and storage. Over time, the CPU got smart enough to handle memory and graphics communication on its own, which made the North Bridge unnecessary, so it got absorbed into the processor. What's left today is a single chip that Intel calls the Platform Controller Hub, and it handles everything the CPU doesn't want to deal with directly. That's why the chipset letter matters when you're buying a board. Take Intel's 700 series. A Z790 board gives you overclocking support, up to 28 PCIe lanes from the chipset, and a pile of USB and storage options. A B760 board uses the same socket, runs the same processors, but cuts the PCIe lanes roughly in half, drops overclocking entirely, and strips back the USB count. Same CPU, noticeably different board. So when someone says just get a cheaper motherboard, it doesn't matter, what they're really telling you is that they've never tried running 3 NVMe drives and a capture card on a budget chipset. It matters. It just matters quietly until the day it doesn't. DIMM slots. If you've ever put two RAM sticks into a motherboard side by side and wondered why your system felt slower than it should, you already know why this section exists. Those long, narrow slots next to the CPU socket are your DIMM slots, and the way you populate them changes how your memory performs. Most motherboards have 4 of them, arranged in 2 pairs for dual-channel memory. Instead of all your RAM data traveling down one 64-bit path to the CPU, dual-channel gives it 2 paths running simultaneously. That effectively doubles your memory bandwidth. But to activate it, you need to install your 2 sticks in the right slots, which is usually the 2nd and 4th slot from the CPU. Put them next to each other in slots 1 and 2, and you're running single channel without even knowing it. Your system will still boot, everything will look fine, and you'll just quietly lose a chunk of performance for no reason. One more thing worth knowing. DDR4 and DDR5 sticks are physically keyed differently, so a DDR5 board won't accept DDR4 modules. You can't force the wrong generation in, which is probably for the best. Voltage regulator module. Your power supply sends 12 volts to the motherboard. Your CPU needs about 1.2. If those 12 volts reach the processor directly, it would be dead before you finished your first boot. The VRM, or voltage regulator module, is the circuit that steps that voltage down and keeps it stable. It's not one component. It's a collection of MOSFETs, chokes, and capacitors arranged around the CPU socket, usually along the top and left edges of the board. Together, they form what are called power phases. Each phase takes turns delivering current to the processor in rapid pulses, and the more phases you have, the smoother and cooler that delivery gets. A board with 4 phases means each one handles a quarter of the workload. A board with 16 phases means each one barely breaks a sweat. This is where the spec sheets start playing games. You'll see boards advertised as 16 plus 2 phase power design, and that first number is the count dedicated to the CPU. But some manufacturers use phase doublers, which split one real phase into 2 separate circuits. You get better heat distribution, but not the tighter voltage control of actual independent phases. A board claiming 16 16 phases might only have 8 real ones with doublers doing the rest. The practical difference shows up under load. Say you drop a high-end processor into a budget board with a weak VRM, under a full workload, the CPU starts pulling serious current. The VRM can't keep up, it gets hot, voltage starts drooping, and the CPU throttles itself down to survive. You paid for a fast processor, and your motherboard is the reason it won't run at full speed. Nobody looks at the VRM when they're shopping for a board. They check the feature list, maybe glance at the price, and call it a day. Then 6 months later, they're on a forum asking why their CPU runs 10 degrees hotter than every benchmark they've seen online. PCIe slots. Your graphics card needs a direct, high-bandwidth line to the CPU, and the PCIe slot is what provides it. These are the horizontal slots running across your motherboard, and they come in different physical sizes, by 1, by 4, by 8, and by 16, where that number tells you how many data lanes the slot has. More lanes, more bandwidth. The by 16 slot is almost always the top one and connects directly to the CPU for the fastest possible link. That's where the GPU goes. The smaller by 1 and by 4 slots handle things like Wi-Fi cards, sound cards, and capture cards. Everything is backward compatible, so you can plug a by 1 card into a by 16 slot and it'll work fine. It just won't use the extra lanes. The part that trips people up is this. A board might have 2 full-length by 16 slots, but only the top one is actually wired with all 16 lanes. The second one could be running at by 4 or by 8 electrically, even though it looks identical. The physical slot size and the actual wiring don't always match, and manufacturers don't exactly put that in bold print on the box. So if you're planning to run 2 GPUs or a GPU plus a capture card, check the manual before you buy the board, not after. M2 slots. Before M2, if you wanted an SSD, you plugged it in with a SATA cable like a hard drive. It worked, but SATA tops out at around 550 megabytes per second, and modern NVMe drives can hit 7,000 or more. M2 slots are what made that jump possible. They're small horizontal connectors built directly into the motherboard that use PCIe lanes instead of the SATA bus, and they accept drives roughly the size of a stick of gum. The standard size is called 2280, which literally just means 22 millimeters wide and 80 millimeters long. You screw one end into a standoff and that's it, no cables, no brackets. The gotcha is that not every M2 slot supports NVMe. Some only run SATA, even though the drive physically fits. You plug in your fast NVMe drive, boot up, and the system doesn't even see it. The motherboard manual is the only way to know for sure which slot supports what. Power connectors. Your motherboard has 2 separate power inputs, and it won't boot without both of them. The big one is the 24-pin ATX connector, usually on the right edge of the board. This feeds power to the chipset, RAM, PCIe slots, fan headers, and basically everything that isn't the CPU. The CPU gets its own dedicated line through the 8-pin EPS connector tucked up in the top left corner. This delivers 12 volts to the VRM, which then steps it down to whatever the processor needs. High-end boards sometimes have 2 of these for overclocking headroom. The classic first build mistake is mixing up the 8-pin CPU cable with the 8-pin PCIe cable meant for graphics cards. They look almost identical. One splits into 4+4, the other into 6+2. Plugging the wrong one in is a fast way to have a very expensive, very bad day. SATA ports. SATA has been running at the same speed since 2009, 6 gigabits per second, which works out to roughly 750 megabytes per second in practice. In a world where everything else on the motherboard has doubled its bandwidth multiple times over, SATA just stayed exactly where it was. That said, it's still on every board. Those small L-shaped connectors along the right edge are where you plug in hard drives, 2.5-inch SATA SSDs, and optical drives if you still have one. Each port takes one cable and connects one device. The thing worth knowing is that some SATA ports share bandwidth with M2 slots. Pop an NVMe drive into certain M2 connectors and 1 or 2 SATA ports quietly disable themselves. It's not a defect, it's a design choice because the chipset only has so many PCIe lanes to go around, and the M2 slot and the SATA port are fighting over the same ones. 15 years at the same speed, and SATA still finds new ways to be complicated. BIOS, UEFI chip, and CMOS battery. Before your operating system even thinks about loading, something has to wake up the hardware and make sure everything is working. That's the BIOS, or on modern boards, UEFI. It's firmware stored on a small chip on the motherboard, and the very first thing it does when you hit the power button is run a self-test. It checks the CPU, the RAM, the storage drives, and if anything fails, it throws an error before Windows or Linux ever gets involved. UEFI replaced the old text-based BIOS with a graphical interface you can actually navigate with a mouse, along with faster boot times and and support for drives larger than 2 terabytes, but it's still doing the same fundamental job. There's one more thing worth knowing. When a new CPU generation launches, older motherboards often need a BIOS update before they'll even recognize the processor, which creates a problem. To update the BIOS, you need a working CPU, but the CPU you just bought won't boot until the BIOS is updated. Some boards solve this with a BIOS flashback feature, a dedicated button on the I/O panel that lets you flash the firmware from a USB drive with no CPU installed at all. If you're buying a new processor for an older board, check whether your board has this before it becomes your afternoon. Next to that chip, there's a small silver disc that looks like a watch battery, because that's exactly what it is. The CR2032 coin cell powers the CMOS, which stores your BIOS settings and keeps the system clock running while the PC is off. When it dies, and it will after about 5 to 10 years, your computer starts waking up thinking it's the year 2000 and forgetting every setting you've ever changed. The fix is a $3 battery from any drugstore. One of the cheapest repairs in all of computing, but endlessly confusing if you don't know it exists. Rear I/O panel. The rear I/O panel is the cluster of ports on the back of the motherboard that face out through the case. This is where all your external connections live. USB ports in various generations, an Ethernet jack, audio outputs, and if your CPU has integrated graphics, display outputs like HDMI or DisplayPort. Higher-end boards add extras like USB-C, Wi-Fi antenna connectors, and sometimes a BIOS flashback button. For years, the I/O panel came with a separate metal shield that you had to snap into the case before installing the motherboard. Everyone forgot it at least once, which meant pulling the entire board back out. It also had razor-sharp edges that would slice your fingers open during installation, which the PC building community treated as a rite of passage. Most modern boards now come with the shield pre-attached, quietly ending one of the most annoying traditions in computer assembly. Front panel headers. This is the part of every first build where someone ends up on Reddit at midnight asking why their power button doesn't work. Somewhere at the bottom of the motherboard, there's a cluster of tiny pins that nobody enjoys dealing with. These are the front panel headers, and they connect your case's power button, reset button, power LED, and hard drive activity LED to the board. The wires coming from your case are individually labeled things like PWR SW, HDD LED, and reset SW, and each one needs to go on a specific pair of pins in a specific orientation. The LEDs are polarity sensitive, so if you put them on backward, they just don't light up. There's no standard layout either. Every manufacturer arranges the pins slightly differently, so you're reading the motherboard manual with a flashlight in one hand and a pair of tweezers in the other, trying to push a connector the size of a fingernail onto a pin you can barely see. Some newer boards include an adapter block that combines all the individual wires into one plug. It's the kind of solution that makes you wonder why it took the industry 40 years to figure out.
Cores. Cores are like the brain cells of your computer's brain. One core can think about one thing at a time, kind of like trying to read a book while cooking noodles. Add more cores, and suddenly your computer can do both at once. Modern CPUs have multiple cores, 4, 6, 8, even 16, each handling a separate task. That's why your game runs smoothly while Chrome eats half your memory in the background. If your CPU were a kitchen, each core would be a separate chef. More chefs mean faster dinner, unless they all try to use the same stove. That's where smart coordination comes in, and that's why multi-core CPUs rule. Threads. Threads are the secret clones of each core. Imagine every chef suddenly learning to work with 2 hands instead of 1. That's threading. Each core can juggle 2 tasks by splitting its attention between them. It's not true multitasking, more like switching between tasks so fast that it feels simultaneous. Intel calls this hyper-threading. AMD calls it simultaneous multi-threading. Same idea, fancy names. Threads make computers better at handling lots of smaller jobs, like running background apps while you're gaming. Think of it as having workers that drink way too much coffee and never stop multitasking. That's what gives your CPU its smooth, responsive magic. Clock speed. Clock speed is your CPU's heartbeat, how fast it ticks, thinks, and gets things done. It's measured in gigahertz, or billions of tiny pulses per second. Every tick is a moment where your CPU performs an action, like moving a file, calculating damage in a game, or loading your cat memes faster. Higher clock speed means more work per second, but also more heat, like running faster on a treadmill. Great for performance, terrible for sweat. Modern CPUs balance their speed automatically, slowing down to save power, or speeding up to handle heavy tasks. So while clock speed matters, it's not everything. It's the rhythm that keeps your CPU's world spinning. TDP. TDP stands for Thermal Design Power. But let's be real, it's just a fancy way of saying how hot this thing gets when it's working hard. It's measured in watts, like a light bulb, but instead of shining, it's screaming internally. A CPU with 65 watts TDP runs cooler and uses less power. One with 125 watts? It's basically a space heater that can play games. TDP helps you choose the right cooler and power supply, because if you pair a high TDP CPU with a weak cooler, you're basically hosting a barbecue inside your case. More watts mean more speed, but also more heat, noise, and possibly regret. Cache size. Cache is your CPU's secret stash of memory, the ultra-fast snack drawer it uses before running to the slower kitchen. Your RAM. When your CPU needs data it uses often, it keeps it here, right next to its brain. Think of it like a student who keeps snacks within reach so they don't have to run to the fridge every 5 minutes. Cache comes in levels, L1, L2, L3, each a little bigger but slower than the last. It's tiny but mighty, the difference between instant action and hang on, let me think. Architecture. Architecture is the blueprint of how the CPU thinks. It's the difference between a medieval castle and a futuristic skyscraper, both built for living, but totally different inside. Intel, AMD, and Apple all design unique CPU architectures that change every few years. These blueprints decide how instructions travel, how data moves, and how efficiently power is used. It's not just about speed, it's about smart speed. New architectures usually mean smaller, faster, cooler chips that do more with less. Think of it like upgrading from an old flip phone to a sleek smartphone. Same purpose, wildly better design. The art of architecture is invisible, but everything depends on it.
Single core. This is where PCs lived before the word multitasking meant anything real. Chips like the Intel Pentium 4 and Celeron D shipped with a single core, and from 2000 to around 2008, that was the entire mainstream desktop. You ran one task. The CPU handled it. When something else needed attention, it waited in line. Gaming in that era worked because games were built around that limitation. Quake 3, Counter-Strike 1.6, and early Call of Duty titles were all designed for single-threaded processors. The hardware and the software were speaking the same language. Today, that language is extinct. Windows 11 will not install on a single-core processor. Microsoft set dual-core as the minimum requirement. If you somehow force a modern OS onto a single-core machine and try to run anything, Chrome with 3 tabs open will pin the CPU at 100%. Gaming is not a conversation at this tier. It's a physical impossibility. The Pentium 4 had a clever trick on some models called hyper-threading, which made the chip appear to Windows as 2 logical processors. It helped. It did not solve the problem. A single-core CPU in 2026 is a museum artifact that somehow still boots. It belongs in a display case next to a floppy disk drive, not in anyone's PC build. Dual core. Chips like the Intel Pentium Gold G7400 and Celeron G6900 ship with 2 cores, and back in 2016 that was acceptable. Web browsing, office work, YouTube, light indie games, nothing demanding. Today, running a modern game on 2 cores is not a budget compromise, it's a hardware conflict. Modern games split their workload across multiple threads simultaneously. Physics, AI behavior, asset streaming, game logic, audio processing. When you only have 2 cores, all of that competes for the same 2 lanes. The CPU maxes out before the GPU even gets the data it needs to draw a frame. You can install a brand new RTX 5070 in a 2-core system and it will sit at 40% utilization while the CPU screams at 100%. The graphics card is ready, the processor isn't delivering, even lightweight esports games become inconsistent. Valorant will technically load, but run Discord at the same time, and the frame pacing falls apart. The average FPS might look fine on screen. What you'll actually feel is lurching, stuttering gameplay that no settings change will fix. If someone is selling you a PC with a 2-core processor in 2026, they're selling you a paperweight with a fan attached. This tier lives in office checkout kiosks, light browsing machines, and as a reminder of how far the floor has risen. Quad core. Between 2018 and 2021, 4 cores was the budget standard for gaming. Chips like the Core i3-10100F and Ryzen 3 3300X handled 1080p gaming solidly. You could run Fortnite, Rocket League, and older AAA titles at respectable frame rates without breaking your budget. For a lot of people, this was the CPU that made PC gaming affordable, but game engines assumed more headroom faster than anyone expected. Today, a 4-core CPU can still technically boot every major game. What it cannot do is run them without becoming the bottleneck. In games like Cyberpunk 2077, Baldur's Gate 3, or any open-world title running dense AI simulations, all 4 cores hit 100% usage and stay there. Your GPU drops to 50 or 60% utilization because the processor can't queue frames fast enough. Frame rates aren't just low, they're inconsistent in a way that settings cannot fix. Streaming while gaming? Not possible. The CPU handling the game is already maxed. Add an encoder on top of it and the whole thing collapses. Competitive esports titles at low settings still work. CS2 and Valorant stay playable when nothing else is running. gaming. But the moment a newer title pushes real CPU workloads, or the moment you try doing anything else simultaneously, you'll hit the ceiling immediately, and it's a hard ceiling. In 2026, 4 cores is the floor for gaming, not a comfortable floor. A floor with serious cracks running through it. HEXA core. Between 2020 and 2022, 6 cores hit the exact right balance for gaming. Chips like the Ryzen 5 5600, i5 12400F, and i5 13400F were some of the most recommended CPUs of their generation, and they have aged remarkably well. Unexpectedly well, honestly. At 1080p, 6 cores handles virtually everything in 2026. Esports games never stress it. AAA games maintain strong frame rates. CPU-intensive titles like Cyberpunk don't drag it to 100% the way they punish 4-core chips. This is where the real controversy lives. The PC building community spent years arguing that 6 cores would age badly by now. For pure gaming, it hasn't. Most modern games still don't meaningfully use more than 6 to 8 threads. The frame rate difference between a Ryzen 5 5600 and a 12-core Ryzen 9 5900X in gaming benchmarks is often under 5%. The wall shows up the moment you try to do more than one thing. Streaming while gaming, your encoder fights the game for CPU time. You'll drop frames in your stream well before you drop them in your game. Running a Blender render in the background, forget it. Content creation at this tier is manageable at 1080p and starts dragging at 4K. The processor is not the right tool for anyone doing serious media production. If gaming is all you do, 6 cores is still a legitimate build choice in 2026. It won't last another 4 or 5 years without pressure, but right now, it holds. Quick question, how many cores does your CPU have? Drop it in the comments. Octa core. This is the gaming sweet spot, and the Ryzen 7 7800X3D made absolutely certain everyone knows it. Chips like the Ryzen 7 5800X3D, Ryzen 7 7800X3D, and Ryzen 7 7700X deliver everything any game running today will demand from a processor. Physics threads, AI threads, streaming threads, game logic, all of it fits comfortably. The CPU stops being the conversation entirely. In CPU-sensitive titles like Microsoft Flight Simulator 2024, Cities Skylines 2, and Cyberpunk at 1080p, where the processor is the actual bottleneck, 8 strong cores with high single-threaded performance pull ahead of everything. The 7800X3D's 96MB 3D V-cache kept it at or near the top of gaming benchmarks for 2 consecutive years, regularly outperforming chips with twice the core count in most games. One thing worth addressing directly, Intel's hybrid architecture complicates this tier. A Core i7 13700K has 16 total cores on paper, but 8 of those are efficiency cores built for background tasks, not the primary game thread. For gaming, what actually moves frame rates is performance core count and clock speed. A chip advertising a high total core count is not the same as one with 8 strong performance cores running at 5 GHz. Don't let the number fool you. For content creation, 8 cores works but shows its limits. 1080p and 1440p video editing runs smoothly. Complex Blender scenes and long 4K exports take patience. Streaming while gaming is fully manageable at this tier. The encoder runs, the game runs, and they don't compete for the same resources. For most gamers, 8 cores is the right answer. Everything above this is for people who need the CPU to do more than play games. 12 core. This is where gaming stops being the constraint and your workload becomes the new ceiling. Chips like the Ryzen 9 5900X, Ryzen 9 7900X, and Core i7 12700K sit at 12 cores, and at this point, no game in existence will push this processor anywhere near its limit. Multitasking stops being a concern. Gaming while streaming, recording gameplay, and running your full desktop setup at once, the CPU handles all of it without any task squeezing the others. Content creation at 12 cores is where work starts feeling genuinely fast. 4K video editing in Premiere Pro becomes noticeably more fluid. Blender render times drop compared to 8-core configurations. If you produce content alongside gaming, this tier removes the CPU from your list of problems. The honest trade-off: gaming alone will never justify this core count. The benchmark differences between a 12-core Ryzen 9 5900X and an 8-core Ryzen 7 5800X in most games land in single-digit percentages. You are spending meaningfully more money for frame rate gains you often cannot see. But if you stream at professional quality, edit videos for clients, or run heavy developer tools alongside gaming, 12 cores earns its cost quickly. 16 core. This is where gaming and serious professional work stop competing with each other. Chips like the Ryzen 9 7950X and Core i7 13700K sit at 16 cores, and the CPU effectively becomes the last thing you'll think about upgrading for years. For pure gaming, you will see no improvement over 8 cores. Zero meaningful frame rate difference in any title running today. Those extra cores are completely invisible to games. For everything else, the ceiling disappears. 3D rendering in Blender or V-Ray cuts times dramatically compared to 8-core setups. Compiling large codebases takes seconds. Running virtual virtual machines alongside your primary workload becomes invisible overhead. Complex audio production with hundreds of plug-in tracks runs without a hiccup. This is the tier for people whose PC is a work tool, not just a gaming device. Content creators doing professional client work, architects rendering BIM projects, developers running multi-environment builds, all of them will use those 16 cores daily and feel the difference constantly. Spending this much purely to game faster is a mistake. Spending it because your work demands it is simple math. 32 core. Chips like the Ryzen Threadripper 9975WX and Threadripper 7970X exist in a completely different category from everything above. This is not a gaming processor. Nobody should buy it for gaming. Pair a 32-core Threadripper with any gaming GPU and your frame rates will be identical to what an 8-core chip delivers. Games do not know what to do with the extra 24 cores, and they don't try. What 32 cores actually does is collapse timelines in professional environments. Architecture studios cut complex BIM rendering from days to hours. Video production companies process multiple 8K streams simultaneously and stop waiting on exports. Software teams compiling large enterprise codebases go from minutes to seconds. The platform itself is designed differently. More memory channels, more PCIe lanes, larger RAM capacity support. These are not gaming rigs with extra cores attached. They are workstation machines with a completely different infrastructure built around them. In the right environment, a 32-core Threadripper system pays for itself in billable hours. Render time is money. If you're not already listing the specific workflows that would eat these cores alive, this tier isn't for you. 64 plus core. Processors like the AMD EPYC 9554 with 64 Zen 4 cores or the Threadripper Pro 9095WX with 96 cores exist in a world where desktop gaming and most professional creative work stop being useful comparisons. These are data center processors and enterprise workstation chips, running hundreds of virtual machines on a single socket, training large AI models on local hardware, managing rendering farms for Hollywood VFX pipelines, operating cloud infrastructure where downtime costs thousands of dollars per hour. The EPYC 9554 ships with 12-channel DDR5 memory, 128 PCIe 5.0 lanes, and error-correcting memory designed to run continuously for years without failure. It doesn't boost to 5 GHz. It doesn't need to. It runs 128 threads simultaneously with a stability profile no desktop chip approaches. For gaming, your games won't run better, your frame rates won't improve, your load times won't change. These processors cost several thousand to tens of thousands of dollars, and in enterprise environments where compute throughput translates directly to revenue, every dollar earns back. If you're curious about whether you need 64 plus cores, you don't. And if you don't already know exactly what you'd put all 64 cores to work doing, you definitely don't.
Capacity. Capacity is how much data your RAM can hold at one time. Think of it as working space for your computer. When you open a program, the computer copies the files it needs from your storage drive into RAM because RAM is much faster to access. Common sizes are 8 GB, 16 GB, 32 GB, and 64 GB. More capacity means you can run more programs simultaneously without your computer slowing down. It does not make individual programs run faster. When you run out of RAM, your computer starts using your storage drive as backup memory, which is called swapping or using a page file. Storage drives are much slower than RAM, so when this happens, you'll notice stuttering, freezing, or programs taking a long time to respond. For basic use like web browsing and simple office work, 8 GB is enough. For gaming and general productivity tasks, 16 GB is the sweet spot. For heavy workloads like video editing, 3D rendering, or running virtual machines, you'll want 32 GB or more. One common misconception: unused RAM is not wasted RAM. Your operating system actively uses available RAM to make your computer run smoother by keeping frequently used files ready to access. DDR. DDR stands for double data rate. It means the memory sends data twice per clock cycle, on both the rising and falling edges of the electrical signal. This doubles the amount of data transferred compared to older single data rate memory. Each DDR generation is physically and electrically different from the others. DDR4 and DDR5 use different voltages, different signal speeds, and different internal designs. Your motherboard supports only one DDR generation. You cannot use DDR5 RAM in a DDR4 motherboard, and you cannot use DDR4 RAM in a DDR5 motherboard. The physical notch on the bottom of the RAM stick is in a different position for each generation, so you literally cannot insert the wrong generation into your motherboard slots. Each new generation brings improvements. Speeds get higher, power efficiency improves, and new features get added. Speed. RAM speed represents how many data transfers happen per second. You'll see two terms used: megahertz and megatransfers per second. The RAM's internal clock actually runs at a certain megahertz speed, but because of the double data rate technology, it transfers data twice per clock cycle. So the effective transfer rate, measured in megatransfers per second, is double the actual clock speed. A stick rated at 3200 megatransfers per second has an internal clock running at 1600 megahertz. The number on the RAM packaging is the megatransfers per second value, which is what matters for performance. For DDR4, common speeds are 3200 or 3600. For DDR5, common speeds start at 4800 and go up to 6400 or higher. Faster RAM helps most with CPU-intensive tasks, games running at high frame rates or low resolutions, and systems using integrated graphics. Integrated graphics share your system RAM instead of having dedicated video memory, so they benefit significantly from faster RAM. There are diminishing returns with RAM speed. Going from 2400 to 3200 makes a noticeable difference. Going from 3200 to 4000 makes a much smaller difference. The performance gains get smaller as speeds increase. Similar to going from a 60 to 144 Hz monitor, you definitely notice it, but going from 240 to 360 Hz, barely noticeable. Your RAM speed is limited by two things: your CPU's memory controller and your motherboard support. Both must support the speed you want to run. If your CPU only supports up to 3200, then even if you install 4000 speed RAM, it will only run at 3200. Channel. A memory channel is a data pathway between your CPU and RAM. Single channel means one RAM stick installed. Dual channel means two matched RAM sticks installed in the correct slots. You can have the same total capacity in single channel or dual channel, but dual channel provides double the bandwidth. For example, one 16GB stick gives you single channel, two 8GB sticks give you dual channel with the same 16GB total, but with twice the data transfer bandwidth. The performance benefits are real. In games, you'll see higher frame rates and smoother gameplay. The biggest benefit shows up in what's called 1% lows, which are the minimum frame rates during gameplay. Higher 1% lows mean less stuttering and a smoother experience. Systems with integrated graphics see massive improvements from dual channel because the integrated GPU is fighting for the same memory bandwidth as the CPU. Always use two sticks when possible. Install them in the correct slots, usually the second and fourth slots on a 4-slot motherboard. Check your motherboard manual to confirm which slots enable dual channel. Timings. RAM timings measure how long the RAM waits before responding to a command. These are measured in clock cycles. When your CPU asks for data, there's a small delay before the RAM starts sending it. That delay is what timings measure. CAS latency, written as CL, is the most important timing number. It represents the delay between when the memory controller requests data and when the RAM starts delivering it. Lower CL numbers mean faster response. CL16 is faster than CL18. CL30 is faster than CL36. Speed and timings work together to determine actual performance. You need to consider both. A 3200 speed kit with CL16 timings might perform similarly to a 3600 speed kit with CL22 timings because the higher speed is offset by the slower timings. You'll see timings listed as a sequence of 4 numbers like 16, 18, 18, 38. The first number is CAS latency. The other 3 represent other delay measurements inside the RAM, but CAS latency is what matters most for comparing RAM kits. For most users, timings make a small difference compared to speed and capacity. For everyday use and even regular gaming, the difference between CL16 and CL18 at the same speed is barely noticeable. XMP or EXPO. XMP and EXPO are pre-made performance profiles stored directly on your RAM sticks. Without enabling these profiles, your RAM will not run at the speed you paid for. All RAM has a base speed set by the industry standard called JEDEC. For DDR4, that base speed is 2133. For DDR5, it's 4800. When you first install RAM, it runs at this slow base speed even if you bought 3600 or 6000 speed RAM. The faster speeds are technically overclocked speeds, and you must enable the profile to unlock them. XMP stands for Extreme Memory Profile and was created by Intel. EXPO stands for Extended Profiles for Overclocking and was created by AMD for DDR5. They do the same thing, but use different standards. Enabling the profile in your motherboard BIOS automatically sets the correct speed, timings, and voltage all at once. The manufacturer has already tested these settings extensively, so they're safe and stable. This is not optional if you want to use the speed you paid for. If you buy 36,000 speed RAM and never enable XMP, your RAM runs at 2133, and you've wasted your money. The process is simple. Restart your computer, enter the BIOS, find the XMP or EXPO setting, enable it, save, and exit. Your RAM will now run at full speed. Form factor. Form factor is the physical size and shape of the RAM stick. DIMM stands for Dual Inline Memory Module and is the full-size RAM used in desktop computers. SO-DIMM stands for Small Outline Dual Inline Memory Module and is the smaller version used in laptops. SO-DIMM is about half the length of a regular DIMM. Laptops use SO-DIMM because of space constraints. Some very small desktop cases, like mini ITX builds or compact PCs, also use SO-DIMM to save space. These are not interchangeable. Desktop motherboards have DIMM slots. Laptop motherboards have SO-DIMM slots. When buying RAM, make sure you're getting the correct form factor for your system. Voltage. Voltage is the electrical potential supplied to the RAM. Standard DDR4 runs at 1.2 volts. When you enable XMP on DDR4, it typically increases to 1.35 volts. DDR5 runs at around 1.1 volts standard. Higher voltage allows the RAM to run at higher speeds and tighter timings. This is handled automatically when you enable XMP or EXPO. For the average user, voltage is not something you need to worry about. It's relevant mainly for stability when overclocking or for enthusiasts manually tuning their RAM for maximum performance.
CUDA cores or stream processors. If your CPU has a few strong workers lifting heavy boxes, your GPU has thousands of tiny workers passing buckets down a line. Those tiny workers are called CUDA cores on NVIDIA cards and stream processors on AMD cards. Different names, same job. They crunch numbers, and they do it in massive groups all at once. A mid-range GPU might have a couple thousand of them. A high-end one, over 16,000. The reason GPUs need so many is because graphics work is highly repetitive. Millions of pixels all need similar math done to them at the same time. Instead of one big brain solving problems one by one, the GPU throws an army of small brains at the problem all at once. More cores generally means more raw power, but only if the rest of the card can keep up. VRAM. VRAM stands for video RAM, and it's the GPU's own personal chunk of memory, completely separate from your system RAM. This is where the GPU stores everything it needs quick access to. Textures, frame data, geometry, lighting maps, all the visual information that makes up what you see on screen. The more VRAM you have, the more data the GPU can hold without constantly going back and forth to slower storage. At 1080p, 8 GB is usually plenty. At 4K, with high-resolution textures and mods stacked on top, even 12 GB can start to feel tight. VRAM also comes in different types: GDDR6, GDDR6X, and the newer GDDR7. Each generation is faster than the last, which means data moves in and out quicker. Think of VRAM like a desk. The bigger it is, the more work your GPU can spread out and handle without slowing down. Memory bus width and bandwidth. Memory bus width is the road between your GPU and its VRAM. A 128-bit bus is like a 2-lane road, fine for light traffic. A 256-bit bus is a highway. A 384-bit bus, that's a full-on autobahn. The wider the bus, the more data can travel at once. But width alone doesn't tell the whole story. What really matters is bandwidth, which is the total amount of data the GPU can move per second. Bandwidth is determined by the bus width combined with the memory speed. So a card with a narrow bus but very fast memory might match the bandwidth of a card with a wider bus and slower memory. Where this really shows up is at higher resolutions. 4K pushes a lot of data, and if the bandwidth can't keep up, the GPU stalls waiting for information. When you see a card with tons of VRAM but a narrow 128-bit bus, that's a red flag. It's like having a massive warehouse connected by a single dirt road. Quick question, what GPU are you running? Let me know in the comments. Clock speed. Clock speed on a GPU works a lot like it does on a CPU. It's how fast each core ticks through its work, measured in megahertz. Every GPU has 2 clock speeds, a base clock and a boost clock. The base clock is the guaranteed minimum, the speed the card runs at under normal conditions. The boost clock is the higher speed the GPU reaches when it has enough power and isn't overheating. Think of it like cruise control versus flooring it on an empty highway. The card speeds up when it can and backs off when it needs to. But here's the thing, clock speed matters less on a GPU than it does on a CPU, because GPUs rely on thousands of cores working together. Core count and architecture design usually have a bigger impact than raw speed. Architecture and process node. Architecture is the blueprint of how a GPU is built, how its cores are organized, how data flows, and what features it supports. NVIDIA's Ada Lovelace, AMD's RDNA 3, Intel's Battlemage, these are all architecture names, and each one represents a different design philosophy. Two cards can have similar core counts and clock speeds, but perform very differently because of how their architectures handle work behind the scenes. Tied to architecture is the process node, the size of the transistors on the chip, measured in nanometers. Smaller transistors mean more of them fit on the same chip, and they tend to use less power and produce less heat. Going from a 7-nanometer design to a 4-nanometer one doesn't just make the chip a little better, it often results in a significant jump in both performance and efficiency. That's why architecture upgrades usually matter more than raw spec bumps. RT cores. Ray tracing is a way of simulating how light behaves in the real world, bouncing off surfaces, casting shadows, reflecting in mirrors, passing through glass. It looks incredible, but it's also extremely demanding. Doing all that light math on regular GPU cores would tank your performance. That's where RT cores come in. They're dedicated hardware built specifically to handle ray tracing calculations. NVIDIA calls them RT cores. AMD calls them ray accelerators. Both do the same thing. Take the heavy ray tracing workload off the regular cores so the card doesn't grind to a halt. Even with dedicated hardware, ray tracing is still one of the most demanding things a GPU can do. That's why it's almost always paired with some form of upscaling technology to keep frame rates playable. Without RT cores, enabling ray tracing in a modern game would drop your frames so hard, the game would feel like a slideshow. Tensor cores and AI upscaling. Tensor cores are specialized processors on the GPU designed to handle AI and machine learning tasks at high speed. For most people, the biggest benefit is AI upscaling. Technologies like NVIDIA's DLSS, AMD's FSR, and Intel's XESS. The idea is simple. Instead of rendering a game at full resolution, the GPU renders it at a lower resolution and then uses AI to reconstruct the missing detail. The result looks almost identical to full resolution, but runs significantly faster because the GPU is doing less brute force rendering. It's like sketching a rough draft and having an AI artist fill in the fine details for you. Tensor cores are also used outside of gaming. Things like AI image generation, video generation, and machine learning workloads. Not every GPU has tensor cores, but cards that do tend to handle AI-related tasks much more efficiently. TFLOPS. TFLOPS stands for teraflops, and it measures how many trillions of floating point operations the GPU can perform per second. In plain terms, it's a raw number that tells you how much math the GPU can crunch. Higher TFLOPS generally means more compute power, and you'll often see this number in marketing material as a headline spec. But here's the catch. TFLOPS is only a useful comparison within the same architecture. A 30 TFLOPS card from one generation might trade blows with a 15 TFLOPS card from a newer generation. It's like comparing two cars by horsepower alone. One might have more on paper, but the other is lighter and handles better. Treat TFLOPS as a rough indicator, not a scoreboard. TDP. TDP stands for thermal design power, and just like with CPUs, it tells you roughly how much heat the GPU puts out under load, measured in watts. But GPU TDP numbers tend to be much higher. A mid-range card might sit around 150 to 200 watts. A high-end card can pull over 350. That's a lot of heat, which means you need good airflow, a decent cooler, and a power supply that can actually handle the load. Modern GPUs also need dedicated power cables cables from your PSU. Older cards used 6 or 8-pin connectors, while newer high-end models use the 12-volt high power, or 12-volt 2x6 connector, which handles more power through a single cable. Every new generation tends to get either more powerful at the same wattage, or more power-hungry for more performance, sometimes both. If you pair a high TDP card with a weak power supply, expect shutdowns, crashes, or a very unhappy system. TMUs and ROPs. TMUs and ROPs are two specs that almost never make it into marketing material, but they're working hard behind the scenes every time your GPU renders a frame. TMUs, texture mapping units, take flat images, called textures, and wrap them onto 3D surfaces. Every wall, floor, character skin, and blade of grass you see in a game has a texture applied by the TMUs. ROPs, render output units, handle the final step, taking all the process data and turning it into the actual pixels on your monitor. More TMUs means textures get applied faster. More ROPs means the card can push more pixels per cycle, which matters most at higher resolutions. Both usually scale with the core count. A GPU with more CUDA cores or stream processors will typically have more TMUs and ROPs as well. You rarely need to compare these directly, but if two cards seem similar on paper and one performs better at 4K, the ROP count might be the reason. PCIe version, Peripheral Component Interconnect Express, is the connection between your GPU and your motherboard. It's the data highway that everything flows through, from game assets to compute tasks. PCIe 3.0 offered around 16 gigabytes per second on a 16-lane slot. PCIe 4.0 doubled that, and PCIe 5.0 doubles it again. Most modern GPUs use PCIe 4.0. That said, if you're building a new system, having PCIe 4.0 or 5.0 support gives you headroom for future cards that might demand more.
GDDR1.
Every GPU needs memory, a place to store all the image data it processes every second. GDDR, which stands for Graphics Double Data Rate, is the type of memory built specifically for that job. It was first introduced commercially by Samsung in 1998, originally called DDR-SG-RAM, Synchronous Graphics RAM with double data rate transfers. The name GDDR came later, but the idea was the same. Standard computer memory was too slow and too general for what graphics cards needed. GDDR ran at modest clock speeds by today's standards, built on the same foundational technology as early DDR SD-RAM, and could transfer data twice per clock cycle, once on the rising edge of the signal, once on the falling edge. The first GDDR1 graphics card was the GeForce 256, later followed by the GeForce 3 and then the ATI Radeon 8500. For its time, that was a meaningful step forward. It proved that GPUs needed their own dedicated memory type, built around raw bandwidth above everything else.
GDDR2.
GDDR2 arrived in 2002. It pushed clock speeds higher and reached up to around 1 gigatransfers per second, meaning roughly 1 billion data transfers per second, which translated to about 4 gigabytes per second of bandwidth per chip. On paper, that was an improvement. In practice, GDDR2 ran at a higher voltage than the original, which generated significantly more heat. Cards using it ran hot, consumed more power, and the thermal problems were difficult to manage. The GeForce FX 5800 was the first to use GDDR2, but ran ridiculously hot. The FX 5800 Ultra had the same problem. GPU makers moved away from it quickly. GDDR2 had a short lifespan, not because it was slow, but because the heat cost was simply not worth the speed gain. By the way, which GDDR generation does your GPU use? Let me know in the comments, and if you are not sure, download GPU Z. It is free and shows you the exact memory, or simply Google your GPU model name and check the specs.
GDDR3.
GDDR3 launched in 2004 and solved the main problem GDDR2 had. It ran at a lower voltage, which meant much less heat and better power efficiency. Bandwidth improved to up to 8 gigabytes per second. GPU makers adopted it widely, and it stayed relevant for years. It also appeared in mainstream consumer hardware in a significant way. The Xbox 360 used 512 megabytes of GDDR3 as its unified system and graphics memory, and the PlayStation 3 used 256 megabytes of GDDR3 dedicated to its GPU alongside a separate pool of system memory. That means even people who never owned a gaming PC had GDDR3 running inside their living room. It was the first GDDR generation to achieve truly broad adoption across both high-end graphics cards and mass-market consumer electronics. The GeForce FX 5700 Ultra was technically the first card with GDDR3, but it wasn't official. Third-party manufacturers just swapped the memory in, and NVIDIA themselves made it official later with the GeForce 6800 Ultra.
GDDR4.
GDDR4 came out in 2006. It offered slightly higher bandwidth than GDDR3, reaching up to around 9 gigabytes per second. The improvement was real, but modest. NVIDIA chose not to use it at all. AMD used it in a small number of graphics cards from the Radeon HD 2000 family, specifically the HD 2600 XT, and certain configurations of the HD 2900 XT and HD 2900 Pro. Then, GDDR5 arrived shortly after and made GDDR4 immediately obsolete. It never had the chance to establish itself. Most people in the GPU space refer to GDDR4 as the forgotten generation. It existed, it worked, but it left almost no lasting impact on the industry.
GDDR5.
GDDR5 launched in 2008 and 2009, and it dominated the industry for close to a decade. The reason it lasted so long was a fundamental change in how data was transferred. Previous generations moved data twice per clock cycle. GDDR5 moved data 4 times per clock cycle, something called quad data rate. That allowed it to reach up to 32 gigabytes per second while running at similar clock frequencies. Almost every major GPU from 2009 through around 2018 used GDDR5. It powered NVIDIA's GTX 900 series, AMD's RX 400 and 500 series, and the PlayStation 4, which used 8 gigabytes of GDDR5 as both its system and graphics memory in a single unified pool. No other GDDR generation has matched its combination of lifespan, adoption, and real-world reach.
GDDR5X.
GDDR5X was introduced in 2016, developed by Micron. It was not a full new generation. It was a targeted upgrade to GDDR5, designed to push speeds higher, while GDDR6 was still being finalized. It reached up to around 14.5 gigatransfers per second, and nearly 58 gigabytes per second of bandwidth. NVIDIA used it in the GTX 1080 and the Titan XP. AMD did not adopt GDDR5X at all, and it appeared in only a handful of products overall. Its main contribution was proving that much higher data rates were achievable, which helped define what GDDR6 would need to deliver.
GDDR6.
GDDR6 released in 2018 and quickly became the standard across the entire industry. It reached up to 20 gigatransfers per second and around 80 gigabytes per second of bandwidth per chip, a large step beyond GDDR5X, while actually being more power efficient. NVIDIA used it across the RTX 20 series and the mid-range and entry-level RTX 30 series. AMD used it across the RX 5000, 6000, and 7000 series. Intel used it in their Arc graphics cards. In 2026, GDDR6 is still found in a large portion of mid-range and budget GPUs. 8 years of continuous deployment makes it one of the most successful GPU memory standards since GDDR5.
GDDR6X.
GDDR6X launched in 2020, again developed by Micron, used exclusively in NVIDIA's high-end RTX 30 series, and later the RTX 40 series flagship cards. AMD did not adopt GDDR6X. The key change was how data was encoded onto the signal. Standard GDDR memory uses 2 voltage levels to represent a 0 or a 1. GDDR6X introduced a method called PAM4, Pulse Amplitude Modulation 4. which uses 4 distinct voltage levels instead of 2, allowing 2 bits of data to be encoded per signal cycle. That pushed speeds to around 23 gigatransfers per second and up to 92 gigabytes per second. The trade-off is that managing 4 voltage levels requires higher precision, and this can cause instability in some hardware configurations under heavy load.
GDDR7.
GDDR7 was standardized in early 2024 and first appeared in consumer GPUs in early 2025 with NVIDIA's RTX 50 series. It starts at 28 gigatransfers per second in first-generation products, with 32 gigatransfers per second chips already in mass production, and the roadmap extending toward 48 gigatransfers per second. It uses a signaling method called PAM3, which works with 3 voltage levels rather than GDDR6X's PAM4. Fewer levels means the signal is easier to interpret cleanly, which results in better stability and noise tolerance. On the RTX 5090, which pairs GDDR7 with a wide 512-bit memory bus, total bandwidth reaches around 1.79 terabytes per second. GDDR7 is also roughly 20% more power efficient than GDDR6 and includes built-in error correction, which matters more as GPUs take on heavier AI workloads. As of early 2025, GDDR7 remains a NVIDIA exclusive in consumer graphics. AMD's RX 9000 series, launched in the same period, still uses GDDR6.
2GB VRAM. This is where gaming GPUs existed a decade ago, and where they struggle to survive today. Cards like the old GT 1030 and ancient GTX 750 came with 2GB, and back in 2014, that wasn't a disaster. You could run League of Legends, Counter-Strike, and lighter titles without your screen turning into a blurry mess. Today, it's borderline unusable. Modern game engines assume you have way more memory than this. When you boot up a 2024 or 2025 title with 2GB VRAM, textures refuse to load properly. You'll see low-resolution placeholder graphics, constant stuttering as the GPU desperately swaps data in and out, and frame drops that make gaming feel more like watching a broken GIF. Even esports titles that are supposed to run on anything will complain. Valorant might technically boot, but you'll be playing on the absolute lowest settings with textures that look like they belong in a mobile game from 2012. The GPU itself might be capable of rendering frames, but without enough memory to store the visual data, performance falls off a cliff. If you're looking at a GPU with 2GB VRAM in 2026, you're essentially looking at electronic waste. It won't game, it won't edit, and it barely functions for anything beyond displaying your desktop. This tier exists purely as a reminder of how far we've come. 4GB VRAM. Around 2018 to 2019, 4GB felt like the sweet spot for budget gaming. Cards like the GTX 1650 and RX 5500 XT shipped with this amount, and they handled 1080p gaming reasonably well. You could play Fortnite, Overwatch, and older AAA titles on medium settings without major issues, but modern games have moved on aggressively. Today's AAA titles are built with high-resolution textures that assume you have significantly more VRAM. When you try running something like Starfield or Hogwarts Legacy on a 4GB card, the game will technically launch, but you'll immediately hit a wall. Textures get downgraded automatically, and you'll see constant pop-in where objects suddenly appear in front of you because the GPU couldn't load them in time. At 1080p on medium settings, you can still squeeze playable performance out of esports titles like CS2 or Apex Legends. But anything recent that demands high-quality assets, you're going to struggle. The GPU might have enough processing power to hit decent frame rates, but the moment you try enabling higher texture quality or increasing draw distance, everything collapses. In 2026, 4GB is the absolute floor for gaming, and even then, you're compromising heavily. It's fine for older games or lightweight competitive titles, but if you're planning to play anything released in the last 2 years, you'll spend more time adjusting graphics settings than actually enjoying the game. Quick question, how much VRAM does your GPU have? Drop it in the comments. 6GB VRAM. Between 2018 and 2020, 6GB was the king of 1080p gaming. The RTX 2060, GTX 1066GB, and RX 5600 XT all came with this amount, and they crushed it. You could max out settings in most games at 1080p, dabble in 1440p gaming on medium settings, and never worry about running out of memory. The problem is games evolved faster than anyone expected. By 2023, developers started designing games assuming players had 8 GB or more. Titles like Resident Evil 4 Remake will run on 6 GB, but you'll notice texture quality drops and occasional hitching when the GPU runs out of space. At 1080p, you're still mostly fine if you stick to high instead of ultra settings, but the real killer is modern features. Ray tracing, completely off the table. Frame generation technologies like DLSS or FSR, those add extra memory overhead, and 6 GB just can't handle it. If you own a 6 GB card today, it's still usable, but you're living on borrowed time. It went from being the perfect amount to feeling cramped incredibly fast. 8 GB VRAM. This is where things get controversial. Cards like the RTX 3070, RTX 4060, and RX 6600 XT all ship with 8 GB, and the debate over whether that's enough has never stopped. For 1080p gaming, 8 GB handles almost everything smoothly. You can max out settings in most games, enable ray tracing in lighter titles, and keep background apps running without issues. The problem shows up at 1440p, especially in newer AAA games. Titles like Call of Duty or Alan Wake 2 will push past 8 GB at ultra settings, forcing you to drop texture quality or deal with stuttering. And 4K? Forget it, unless you're fine with medium textures and compromised visuals. The GPU itself might have the horsepower to run these games, but the memory bottleneck kills performance. What makes this frustrating is that many 8 GB cards are genuinely powerful. The RTX 3070 can handle 1440p gaming beautifully, but in certain scenarios, it runs out of VRAM before it runs out of processing power. That's a design choice that angered a lot of people, especially since competing AMD cards at similar prices often came with 12 GB or more. Still, for most gamers playing at 1080p or 1440p without maxing every setting, 8 GB works. It's not future-proof, and you'll need to be mindful of texture settings in demanding games, but it's functional. Just don't expect it to age gracefully. 12 GB VRAM. This is where modern gaming finally feels comfortable. Cards like the RTX 4070, RTX 3060, and RX 6700 XT all ship with 12 GB, and this tier hits the sweet spot for most gamers. At 1080p, you're massively overkill. At 1440p, you can max out every setting without worry. At 4K, you can comfortably run high settings in almost every game. Modern AAA titles are starting to recommend 12 GB for ultra textures and ray tracing. Games like Hogwarts Legacy and Starfield explicitly list 12 GB as the target for optimal visuals. This tier also gives you breathing room for content creation. Video editing at 1080p or 1440p, photo editing with large files, and light 3D rendering all run smoothly. You're not maxing out memory constantly, and multitasking while gaming becomes effortless. For anyone building or upgrading a gaming PC in 2026, 12 GB is the recommendation. It's not overkill, but it's more than enough for the next few years. Even as games continue demanding more memory, 12 GB will handle it without forcing you to compromise on visual quality. 16 GB VRAM. This is where gaming meets professional workflows. Cards like the RTX 4060 Ti 16 GB, RX 7800 XT, and RTX 4070 Ti Super come with this amount, and suddenly limitations disappear. At 4K ultra settings with ray tracing enabled, everything runs smoothly. Heavy texture packs, high-resolution mods, and demanding visual features don't even make the GPU flinch. But the real advantage is for creators. Editing 4K video timelines and running Blender with complex 3D scenes all benefit from having this much memory. You're no longer thinking about whether your GPU can handle something, it just does. For gamers who also stream or record their gameplay, 16 GB removes any worry about multitasking. Running OBS, Discord, a browser with dozens of tabs, and a demanding game simultaneously, no problem. The VRAM can handle all of it without performance dropping. If you're planning to keep your GPU for 5+ years or you do any kind of creative work alongside gaming, 16 GB is the smart choice. It's more expensive up front, but you're buying longevity and flexibility that 8 GB or 12 GB cards simply can't match. 24 GB VRAM. Cards like the RTX 4090, RTX 3090, and RTX 3090 Ti come with 24 gigabytes, and at this point, you're not just gaming, you're rendering, creating, and pushing professional workflows. Every game at 4K Ultra with ray tracing maxed runs flawlessly. But more importantly, creative work thrives. Video editors working with 8K footage or heavy effects no longer worry about memory limits. 3D artists rendering massive scenes in Blender or Unreal Engine can work without constant crashes or slowdowns. For pure gaming, 24 gigabytes is overkill. But if you're a content creator, streamer, or professional who uses their GPU as a primary work tool, this tier makes sense. You stop thinking about what's possible and just work. Projects don't slow down. Apps don't crash. Everything just runs. This is also the tier where your GPU becomes a long-term investment. While 8 gigabytes cards are already feeling pressure, 24 gigabytes will remain relevant for years. 48 plus gigabytes VRAM. Cards like the RTX 6000 ATA with 48 gigabytes exist in a completely different world. These aren't gaming cards, they're professional workstation GPUs designed for studios, research labs, and enterprise environments where downtime costs thousands of dollars per hour. At this level, you're working with Hollywood-level VFX, massive scientific simulations, training large AI models, and running enterprise rendering farms. The RTX 6000 ATA comes with 18,176 CUDA cores, 568 Tensor cores, and error-correcting memory to ensure absolute stability. These cards cost over $7,000, and they're worth every penny in professional environments. For gaming, this does absolutely nothing extra. Your games won't look better. Your frame rates won't magically double. Your loading times won't improve. For 99% of people, this much VRAM is complete overkill. But in professional settings where render times translate directly to revenue, where crashes halt entire production pipelines, and where massive datasets need to fit entirely in memory, 48 gigabytes makes perfect sense. If you're considering this tier and you don't already know exactly why you need it, you definitely don't. Air cooling. Air cooling is the simplest and most common way to keep your computer from turning into a hot potato. It uses metal and fans. That's it. A chunk of metal called a heatsink sits on top of your CPU, and when it gets hot, the metal soaks up the heat like a sponge. Then the fan blows that heat away into the air inside your case, and other fans push it out. Imagine your CPU is sweating, and the heatsink is the towel. Cheap, easy, and reliable. That's air cooling. The only real downside? It's not the quietest. When your computer's under load, those fans sound like tiny jet engines. But hey, it works. No fancy liquids, no risky plumbing, just good old wind power. It's the reason budget PCs and gaming rigs everywhere stay cool enough to survive long nights of Minecraft marathons. AIO liquid cooling. AIO, or all-in-one liquid cooling, is what happens when your CPU gets treated like it's in a sci-fi spa. Inside that sleek-looking unit are tiny tubes filled with coolant, yes, literal liquid, that move heat away from the CPU and send it to a radiator. The radiator has fans that blow the hot air out, kind of like a car's cooling system but shrunken down. The best part? It looks awesome. RGB lights, glowing tubes, all that futuristic flair. But it's not just for show. AIO coolers can handle way more heat than most air coolers, making them perfect for powerful CPUs or overclocking. The trade-off? More parts, more chances for something to go wrong. If an air cooler fails, you lose performance. If an AIO leaks, well, you might lose a motherboard. Still, for most PC gamers, it's the perfect balance between power, looks, and not needing a wrench to install. Custom water loop. Custom water loops are for the kind of PC builders who look at an AIO cooler and say, cute, but I want danger. These setups are fully custom built. Tubes, fittings, pumps, reservoirs, all carefully pieced together like a mini science lab inside your case. Instead of one sealed system, you build the whole route yourself. Water flows from a tank, through the CPU block, maybe the GPU too, and back to the radiator. It's gorgeous, clear tubing, colorful coolant, and if you add RGB lighting, your PC basically becomes a nightclub for electrons. But it's not just about looks. Custom loops can handle monster levels of heat and keep your PC whisper quiet. The downside, you need patience, tools, and nerves of steel. One wrong fitting, and you might create a very expensive water feature. It's not for beginners, it's for enthusiasts who enjoy risk and beauty in equal measure. Passive cooling. Passive cooling is the chill monk of the PC world. calm, silent, and doesn't need to move a muscle. No fans, no pumps, just pure silent heat dissipation through massive chunks of metal, fins, and clever design. The idea is simple. Heat naturally rises and spreads, so the components slowly release warmth into the air. It's perfect for low-power builds. Think home servers, mini PCs, or systems you want running 24/7 without making a sound. The big perk: zero moving parts. That means nothing can break or make noise. The downside: it's not powerful enough for high-end CPUs or gaming beasts. If you tried to cool a gaming rig passively, you'd probably end up with molten RAM. But for quiet, low-heat machines, it's pure serenity, like a computer meditating while doing your taxes. Immersion cooling. Immersion cooling is when your computer takes a literal bath and survives. The entire motherboard and components are dunked into a special clear liquid that doesn't conduct electricity. This liquid absorbs heat way better than air, so it keeps every part cool and calm, even under insane workloads. It's like your PC living inside a fish tank, minus the fish. And yes, it looks as weird as it sounds. Companies use it for servers or crypto mining rigs that run non-stop because it's super efficient and quiet. But it's not something you do at home unless you enjoy risk and cleanup. Spill it once, and your workspace smells like a chemistry lab. Still, it's one of the coolest and most futuristic methods out there, a PC taking a spa day in liquid armor. Thermoelectric cooling. Thermoelectric cooling is where science decides to flex a little. It uses something called a Peltier module, a tiny plate that gets cold on one side and hot on the other when electricity passes through it. It's like magic, but real. The cold side touches your CPU, soaking up heat, while the hot side dumps it somewhere else, usually with the help of a heatsink or a water loop. Sounds amazing, right? It is, until you realize how much power it eats and how tricky it is to balance. If you don't manage that heat properly, it's like trying to cool your drink by setting your house on fire. Still, it's fascinating tech, the same stuff used in mini fridges or spacecraft. For most PC users, it's overkill, but for experimenters and hardware nerds, it's a fun way to turn science class into a cooling system.